The graph depicts the situation we have for this problem. The actual graph is in the statement of the problem, but keep in mind that h and t are different values because of the slope of the upper wedge. We will only consider the interference between the upper and lower surfaces of the air wedge between the microscope slides. Light will travel more slowly in the glass of the slides than it does in air. Hence, the wave reflected from the upper surface of the air has no phase shift, and the wave reflected from the lower surface has a half-cycle phase shift. Since only one of the reflected waves undergoes a phase shift, destructive interference can be used with the fact that 2t is going to be m times lambda 0, where m equals 0, 1, 2, and so on. If we consider the triangle from up to t, and then the triangle all the way through h, we have a similar triangle. And if we call the distance from here to t x, then by similar triangles we have t over x will equal h over L, and this means that t equals xh over L. And if we take this result and plug it back into the destructive interference formula, we get 2xh over L equals m lambda naught, which means that x equals m lambda naught over times L over 2h. And so this will equal m times 0.1 meters. Lambda naught is 500 nanos over 2 times 0.02 times 10 to the negative 3 meters. And this gives us 1.25 times 10 to the negative 3 meters times m, or the same as 1.25 millimeters times m. And the successive dark fringing that correspond to m equals 1, 2, 3, and so on will be spaced 1.25 millimeters apart for m equals 0. We get x equals 0, which is where the two slides touch at the left hand side of the figure above. Hence, there is a dark fringe at the line of contact.